Welcome to today's paper reading. Today's paper is titled, COD, Learning Conditional Invariant Representation for Domain Adaptation Regression. This paper was published on AR14 by Hao-Ran Yang and colleagues from Sun-Yat-sen University and Jiayin University. The abstract introduces the development of adaptation regression (DR) for complex learning problems. It highlights the challenges posed by the continuity problem in regression, which makes existing methods effective in classification settings inapplicable. The authors establish a sufficiency theory for the regression model, demonstrating that the generalization error can be sufficiently controlled by the cross-domain conditional discrepancy. To address the continuous conditioning variable, a novel conditional operator discrepancy, COD, is proposed, which leverages kernel embedding theory to provide a metric property on conditional distributions. A COD-based conditional invariant representation learning model is then introduced to minimize the discrepancy, with modifications to moment statistics shown to enhance the model's discriminability. Extensive experiments on standard DR datasets confirm the theoretical findings and demonstrate the superiority of the proposed methods over state-of-the-art DR techniques. Deep learning has demonstrated significant success across various applications, largely due to its ability to fit complex models. However, the training of these high-quality models heavily relies on large-scale data with sufficient annotations, which can be costly to obtain. This is particularly challenging for unlabeled data, where annotations are usually expensive. Unsupervised domain adaptation aims to address this issue by reducing training costs through the transfer of knowledge, without the need for labeled data. In the context of unsupervised domain adaptation, UDA, for regression, the primary focus is on scenarios with continuous label variables. The goal is to address the distribution shift between source and target domains and develop models that can be effectively transferred. However, several challenges exist in this domain adaptation for regression (DR) framework. These include the infinite matching problems due to the continuous nature of labels, the risk of negative transfer, and the misalignment of local structures. To tackle these issues, the authors propose a theoretical framework for conditional alignment and introduce a novel metric called conditional operator discrepancy, COD, to measure distribution discrepancy. Additionally, a representation learning model is developed to enhance the discriminability of task-related knowledge during transfer. Figure 1 illustrates the conditional shift in a regression setting, where the label value y ranges from 0 to 1, and the color gradients indicate continuity. In part A, before adaptation, there is a distribution shift between the source and target representations, causing the predictor trained on the source domain to fail in generalizing to the target domain. Part B shows that after marginal distribution alignment, the distributions of the source and target domains are globally aligned. However, representations with different labels may be falsely aligned across domains, leading to significant inconsistency between cross-domain labeling rules. Consequently, the level sets provided by the source predictor are not suitable for target representations. In Part C, after conditional distribution alignment, label-wise matching is achieved. Here, the level sets of cross-domain labeling rules are consistent, and the source predictor becomes reliable. The COD metric is defined to measure the discrepancy between conditional distributions Px, y using first-order and second-order statistics in RKHS. This allows for the alignment of conditional distributions as a whole rather than individually for each y. The empirical estimation of COD leverages the kernel trick to derive a closed-form solution, which is crucial for practical implementation. Additionally, the discriminability of the empirical COD is analyzed to ensure that the representations remain useful for classification tasks. The learning objective for COD-based DR modeling involves minimizing the source risk while aligning both the conditional and marginal distributions, with trade-off parameters lambda1 and lambda2 balancing these objectives. Figure 2 illustrates the conditional operator discrepancy, COD metric, which is crucial for aligning conditional distributions in regression settings. Part A shows how classification domain adaptation, DA, methods handle conditional shift by aligning discrete clusters of Px, y. However, this approach is infeasible for regression due to the infinite possible slices of Px, y. In contrast, Part B demonstrates how COD embeds continuous conditional distributions into reproducing kernel Hilbert space, RKHS, and characterizes them using finite statistical moments. This method does not depend on specific conditions Y. The alignment of conditional distributions is achieved by matching first-order and second-order statistics, represented by the mean embedding operator UX, Y and the covariance operator CXX, Y. Minimizing COD ensures that the level sets of cross-domain labeling rules are aligned, effectively addressing the conditional shift in regression tasks. The experiments were conducted on 3 benchmark datasets, dsprites, BioWeConnect, and MPI3D. Each dataset presents unique challenges and domain characteristics. For instance, dsprites consists of 3 domains with a total of 737,280 images, while BioWeConnect has 2 gender-based domains totaling 15,678 images. MPI3D, a simulation-to-real dataset, includes 3 domains with 1,036,800 images. The evaluation focused on several transfer tasks within each dataset, such as 6 tasks in dsprites and 2 tasks in BioWeConnect. The primary metric used for evaluation was the mean absolute error, MAE, which was summed across subregression tasks to provide a comprehensive performance measure. This approach allowed for a detailed comparison with state-of-the-art domain adaptation methods. Table 1 presents the domain adaptation regression results using mean absolute error, MAE, on the dsprites dataset with a ResNet 18 model. The table shows that COD achieves the best performance among all competing methods in nearly all tasks. Notably, COD demonstrates a significant improvement in the CN and CS tasks, where other methods, including state-of-the-art domain adaptation regression (DR) methods, show much higher error rates. The average MAE across all tasks for COD is 0.134, significantly lower than the other methods, indicating the effectiveness of the conditional invariant representations learned by COD. Table 2 presents the mean absolute error, MAE, results for domain adaptation regression on the BioWeConnect dataset using a ResNet 18 architecture. The table lists the MAE for different methods across 2 tasks, male to female, MF, and female to male, FM. The COD method demonstrates superior performance with the lowest MAE values across both tasks, indicating its effectiveness in handling domain adaptation challenges. The average MAE for each method is also provided, showing COD's overall lower error compared to state-of-the-art methods, thus validating its theoretical and methodological superiority in complex regression tasks. Table 3 presents the mean absolute error, MAE, results for domain adaptation regression on the MPI3D dataset using ResNet 18. The table shows that COD achieves the lowest MAE in the RLT task, outperforming other state-of-the-art methods. Additionally, COD secures the second-best average MAE across all tasks, demonstrating its superiority in domain adaptation regression tasks. The MAE values for various methods are detailed, highlighting COD's competitive performance. Table 4 presents an ablation study on various metrics for domain adaptation regression (DR). The study evaluates different objectives across datasets like dsprites, BioWeConnect, and MPI3D. Key observations include the promising results of OT-based metrics on DR datasets, where conditional alignment with COD outperforms marginal alignment with KGW on MPI3D and BioWeConnect. The study also highlights the necessity of combining KGW and COD for challenging tasks, as well as the effectiveness of rethinking the discriminability of COD, which ensures lower MAE values across all datasets. Overall, the results underscore the importance of conditional alignment in successful DR. Figure 3 presents a TSNE visualization of learned representations, where label values are denoted by color gradients. 8 label values are selected from the range of the variable for visualization. The figure distinguishes between source samples, marked with plus, and target samples, marked with. This visualization helps in understanding the distribution and alignment of features across different domains, providing insights into the effectiveness of the adaptation methods used. Figure 4 presents the mean absolute error, MAE, values under different settings of hyperparameters, specifically lambda1 and lambda2, which are parameters of the modified COD and KGW. The results indicate that the COD-based domain adaptation regression (DR) model demonstrates robustness to various parameter choices. Notably, the MAE values remain stable across random experiments, suggesting that the proposed method is robust both in terms of randomness and parameter settings. This stable performance underscores the empirical reliability of the proposed model. The COD-based domain adaptation regression (DR) method addresses the challenges of conditional shift in continuous output spaces. This method ensures that the cross-domain generalization regression error is sufficiently bounded by the conditional discrepancy on continuous labels. The COD serves as a well-defined metric for measuring conditional discrepancies and for empirical modeling. Additionally, the method includes a discriminability enhancement mechanism. Numerical validations conducted on standard DR datasets demonstrate the superiority of the COD-based approach, highlighting its effective performance in domain adaptation tasks. Thank you for watching.